Hello everyone. We're going to change things up a bit. So far we have been solving one or two or three stages per video, right? I just read through what's required in that stage and just implement it. But now what we're going to do is we're going to read all these stages. We'll read all what is required of us, and then I'll explain all of that through a sequence diagram and then a flowchart. So at least these sequence diagrams and flowcharts are my implementation of it. There can be other implementations of these. So our solution is multi-threaded, right? But actual Redis is single-threaded. So there is a different implementation of this, but this is the solution I came up with, and this is what I'm going to explain. Anyways, the reason I'm doing it this way is because I think it's pretty complicated, and I'm not sure I would be able to give you the bigger picture of what we are trying to implement without just telling you what we are going to implement. I can't show you the bigger picture, the forest for the trees, through code. So I need to explain what's required of us, and that's what I'm trying to accomplish in this video. So let's just read what's required of us. So we're implementing the multi command, right? And the multi command starts a transaction for my Redis server. After a multi-command is executed, any further commands from the same connection will be queued and they are not executed. Alright. The queued commands can be executed using an exec command. In this stage, we'll just add support for handling the multi-command and returning an OK. We'll get to queuing commands in the later stages. No, we're going to do it in the next video, but I'll explain everything about it right here. Okay, so our Redis server, it gets a multi-command from a client. Okay, and what we're going to do when we receive a multi-command is we see this multi-command is for per client basis, right? So any further commands from the same connection will be queued. So somehow I need to mark that a client is in transaction. And we already have a class for our client, right? It's in components, infra, and client. We have this class, and this is representing the connection that they are talking about, right? And I somehow need to mark each and every client that is in transaction. So what we'll do is we'll create a Boolean field in that class, and I'll call it transactional context. So whenever a client connection, we receive a multi command through a client connection, we'll mark that client to be in a transaction by setting this Boolean flag to be true. We'll set it to true. Okay, and after setting it to true, if you read, all the future commands, any further commands will be queued but not executed. So any command after multi that follows the same connection, that is coming down the same connection, they need to be queued and not executed. So we need a data structure to hold all those commands, and voila, queue. So we'll use a queue. All right. As soon as I receive a multi command, I'll initialize a queue for my client. All right. Okay, so that will create our command queue. Okay, so when my transactional context is true, see, we just set it to true, right? So while my transactional context is true, any command that comes down should be queued. But there are exceptions, and the exceptions are the exec and the discard command. Those are special commands. So let's read about the exec command. Alright, the exec command executes all commands queued in a transaction. So we started the transactional context and we initialized a queue, and let's suppose we received 100 commands from the same connection. So all those will now be in this queue. And whenever we receive an exec command, see, exec is special. What it will do is we will not queue that command. Instead, we'll start pulling out of our queue and applying those commands. That's what we need to do. All right. So that's the special exec command. We'll discuss about it. All right. So the other special command is the discard command. So what the discard command will do is it will roll back all the changes. All right. So the state after the discard command should be what the state was before the multi command. Alright. So whenever we receive a discard command, what we can do is we can set the transactional context to false because now the transaction has been rolled back. Alright. And I need to set the queue to null. We need to prepare the queue for the next transaction. Okay. So for any command that is not the exec or the discard command, while the transactional context is true for a client, we will put those all those commands into the queue. See, we'll queue the commands. And if we receive the discard command, we'll set the queue to null and set the transactional context to false. All right. Let's read further. It returns an array of responses. Yeah. So let's read about the discard command first. Discard command is used to abort a transaction. It discards all commands queued in the transaction and returns an OK. All right. So whenever we receive the discard command, we'll set the transactional context to false. We'll set the queue to be null, and then we'll return with an OK to the client. That's what discard command does. All right. Now let's discuss what the exec command is. All right. The exec command executes all the commands that were in the queue. It returns an array of responses of the queued commands. So there will as I told you, let's imagine we have 100 commands in our queue. When we apply those commands have responses. When we send a set command to Redis, Redis responds back with OK or something, right? And let's say we sent 100 set commands in a transaction. So the response of all those 100 set commands should be returned back to the client in a resp array format. All right. So what is an exec without multi? If Redis receives an exec from a connection without having received a multi, we return with an error. All right. Error exec without multi. And same is true for discard. Okay, we can't send discard without having first sent a multi. The Redis will respond back with an error. It will be error discard without multi. And this error should be serialized in the resp simple error format, and that would look like something like this. It's just hyphen error, the error message followed by a /r/n. That's it. All right. So what if we send an exec command right after the multi command? That's a special case. There are no commands in my queue as of yet. So what will the exec command do? If exec is executed right after the multi command, it returns an empty array. Empty array signifies that there were no commands in the queue and the transaction was executed successfully. And an empty array in resp serialized format looks like this. All right. So if we receive an exec right after a multi, we just respond back with this error. All right. If the size of my queue is 0, we respond back with this empty array, empty resp, resp array. All right. We have already discussed what they're asking of us. So when we right here. So when we queue a command, our Redis server is supposed to respond back to the client with this message, this queued message. All right. And the response looks like this. That's just what we need to return for every command that is queued. And now here comes the important part. Executing the transaction, sorry. When the exec command is sent within a transaction, all commands are executed. Yeah, I already told you. So there is nothing special to discuss here. Other thing we need to discuss is what happens if there are failures within our transaction. Okay, so in this challenge, we are not doing something known as rolling back when we see an error within a transaction. Okay. So typically a transaction is thought of like if we get an error, the transaction will roll back. But that only happens in case of Redis if we are watching certain rows. before sending the multi command, before starting the transaction. All right. So if we are watching certain keys and we have errors on those keys, in that case, the transaction can roll back. But in other cases, when we are not watching the keys, in that case, the error, what we return back to the client is, let's say the first command was set. So the response for set would be okay. The second command would be increment, and we cannot increment the string. So the second response is an error. Our transaction did not roll back. In fact, we just returned back the error we got. That's it. That's all we need to do in case of failures. All right. And the last stage here is multiple transactions. So this is important if our Redis server is single threaded. But since our Redis service is multi-threaded and each client is operating on a different thread, right? In that case, whatever I do for one client will be applicable for all the clients, and we'll pass this stage automatically. Now, if it were single threaded, if my implementation was single threaded, then we'd have to add support for multiple clients in a transaction, and that would be implemented via an event loop and an event loop within an event loop, something like that. That's just how I imagine it would be solved, but that's not how we're doing it. So let's get back to the sequence diagram. Okay, so when we will receive an exec command, how I have implemented and chosen to implement this is that we might need to roll back, right? We might receive a discard command, all right, after a multi command. And other thing I have chosen to do is I have created the skeleton to roll back even after an exec command. So if my Redis server receives an exec command, I've added the skeleton, the bare bone structure, for you to be able to extend this project to roll back in case an error happens. All right. How I have done that is, let's just open Excalibur. Okay, so we have a primary data store, right? We have a data store. It's a concurrent hash map. All right, and we have certain keys here. Key is mapped to a value. All right. So yeah, something like this. This is what our store looks like, and there are multiple keys. Key 1, and this can be key 2. All right. The keys are unique. This is what our store looks like. So how I have chosen to implement is that when we have received a multi command, and then when I receive an exec command, let's say my exec command was preceded by a set command. All right. So when we execute the transaction, what we need to do is we need to set another key into the store. All right. Yeah, we need to set another key into the store. But the issue with that is, if we need to roll back, we need to keep track of what all changes we did to the store. And that's a huge issue. We can't keep track of everything. We might have incremented certain integers, we'll then need to decrement them in my store. So what I have done is I have implemented a temporary store as well. Temp store. All right. And what this temp store is, for any command that my exec command is executing from my queue. Let's say the command is working on a key, the value of the key is a, any variable a. So what I will do is, so we are working on a key a. What I have done is, instead of working on the primary store, I am working on the key in this temp store. All right, a. and whatever the value it has. Okay, what I'm doing is I'm not adding it to my primary store right now. I will add it later. Okay, so let's say then I received another command to set b to b1, and then I received another command to increment b. Excuse me, to increment b. So now the value of b should be 2. So now there are three things that need to be rolled back. Now if we had done these changes to my store, my primary store that's in blue right here, then we'll have to do 3 more operations on my store to roll back. But since I'm storing all the temporary data in my temp store, what I can do is I can just discard this temp store. All right. Now since they can, each and every client can execute a transaction, each and every client will need a temp store of its own. So the client class I showed you before, it will feature a boolean flag, it will feature a queue, and it will feature a temporary store. All right. And at the end of the execution of the transaction, when all the commands have been executed, when my queue is now empty, what I can do is I can dump all these values from my temporary store into the primary store. Okay, but there is another problem with that. So let's say these were here right now. Okay, but my Redis server supports multiple clients, and another client has accessed this primary store and added some keys and incremented some values. So let's say it added b to b, a string, whatever. Okay, but my temporary store says the key b is mapped to an integer. So now my stores are out of sync. That's a huge issue. So while a transaction is executing, while I've read some keys from my temporary store into my from my primary store into my temporary store and changed the values to something, I cannot allow other clients to change values here or even read. Let's say we'll block any read and any write to the primary store while a transaction is being executed. All right, what we'll do is instead of we won't allow them to do this. What we'll do is we will add a lock to my primary store while a temporary store is being calculated, and when so this the client that is executing a transaction that will hold the lock for the store. So if that client has the lock to the store, it can dump these values into the store. Okay, and after the values are dumped to the store, only then will I unlock the store. Okay, so that's how a transaction would work. So in case we needed to roll back, what we will do is I'll discard this temp store and just unlock, and now I don't have to change anything for a rollback. Okay, quite simple. So let's see that through a sequence diagram. When I receive an exec command, what I'll do is I'll talk see mm, this is all part of a Redis server. Oh, sorry, this is all part of a Redis server. Okay, this is Redis. Okay, but a Redis has slaves as well. A Redis master node has slave nodes as well. So if my uh, holy shit, what am I doing? Yeah, So this is a master node. My transaction is being executed. And I told you that I will, no, before that, let me tell you that this master node may have slaves as well. Okay. So this may be a Redis slave. Okay. And it is replicating from the master. All right. So I'll show you how the dump process will look like. Again, we need to dump these keys into this store, and this will be replaced by this, and then I'll discard this. I will unlock, but now my Redis slave is out of sync with the store. The store did not have value 2 for key. It had value, and it did not have these keys in its store. But we do need to send these keys down to this slave as well. And this state right here, which is this state, can be replicated on the slave if I pass down all the commands that were required to get to this state of the store. All right, my transaction had some commands. It had 3 commands. It changed the value of it changed the value of key. It added a, it added b, and then it incremented b. So it had 4 commands. So I need to pass those 4 commands down to slave. But the issue is I have pulled all the commands out of my queue and I have used them up. I am not storing those commands anymore. How can I pass them down to a slave? That's a huge issue. So what we'll do is I'll create a copy of the queue. That's just how I thought of doing it. I created a copy of the queue. All right. And I saved it in memory. It's for a short while. And what's this? Transaction cache applier. Okay, let me so this what you see right here is very close to the code, and we'll get back to explaining this, what I'm creating here, what's this transaction cache applier, and what all this is. But the important thing to see is that I copy and then I create something known as a transaction cache applier. It's we'll get to what it is soon enough. But the important thing to see is that I'm locking my primary store. All right. And after locking, I am reading out using a reentrant lock. When I lock my primary hash map, I read the data out into my temporary hash map. All right. I read data. Then this transaction cache applier, what it does is it reads all the commands from the queue and then updates the cached data. Okay, so what this transaction cache applier is doing is it's reading from this temporary hash map and then updating the values as they should be. All right, and it's applying the commands to the cache. It happens in a for loop for all the commands in my queue. So okay, and if the command fails, we can roll back and abort the transaction. But that's not what required of us by CodeCrafters. We don't need to roll back the transaction. Okay, we just need to return back a string, an error string. Okay, and I'm just showing you what can be done, how you can extend this project. It's really not that difficult. After you have followed my next video, it won't be that difficult to change the functionality if you wanted to. That's not required of us. I'm just showing what can be done here. Okay, and after the commands are applied, we will have calculated the response that needs to be sent back to the client, right? Executing a transaction. When we execute a transaction, we return back an array of all the responses, right? Where is it? Empty transaction, failures within a transaction, right here. We respond back with all these messages. Okay, so all these messages also need to be saved somewhere, and again we'll do that in my client class. For each transaction there needs to be a new array. Okay, So we'll add that array in my client. All right, so when we apply those commands, we'll add the response to that array in my client class, and then I can unlock the hash map. After unlocking the hash map, we can use this copy of the local copy of the queue of the commands, and again in a for loop replicate all those commands down to the slaves. We have already done that. We'll just copy paste some code and that will be handled. All right. But in case all commands succeed, what we need to do is we created a temporary hash map, right? Now my primary hash map is unlocked. What I can do is this transaction cache applier, it will dump all the keys from my hash map into my primary hash map. Okay, but there is something else, another edge case that we need to handle. What if instead of only adding and updating the keys, the temporary hash, we are deleting some keys from the primary store. Let me get back to it. All right, so instead of this, what if we need to actually delete this key from the primary store? So after we dump the temp store into the primary store, this key should disappear. All right, and it should only have these two keys. All right, like so. Okay, we need to delete a key, and we had a value class, right? So a key is mapped to a value, and this value just holds the value of the key in a string format, and the created time and the time at which it's going to expire. In here, we'll add another boolean, public boolean to be deleted after transaction. So I will add the key to my temp store, and I'll for the value, this value, I will set this transaction to this boolean variable to be deleted after transaction to be true. And while dumping the temporary store into my main store, one by one I can check if a value is marked to be deleted, I will remove it from my primary store. Okay, so that's how we'll tackle deletions in a transaction. Okay, let's look at the flowchart that I've created. So we start and we receive a multi command. We set transactional context to be true. We initialize the command queue. We receive a command. We check if the transactional context is true. If it's not, we execute the command immediately. But if it is set to be true, we can check if the command that we received is exec or discard. If it's not an exec or discard command, we just add it to the queue and we get back to receiving a command. But if it's an exec or a discard command, the discard command is quite simple, right? We just need to set the transactional context to be false again and set the queue to be null and delete the temp store if calculated. All right. So that will discard the command. But if it's an exec command, we copy the command queue. We use this copy of the command queue to trickle down all the commands down to the slaves. And for each command, we verify, we apply those commands on a temporary store using this transaction cache applier. This applier is a functional interface. It just applies all those commands to this temporary cache in a transaction. That's why I've named it transaction cache applier. Okay, and for each command, this happens after we have locked the original hash map. This cache applier locks the original hash map. It reads the data out from the original hash maps, caches it into the temporary store, applies the incur or the decker command or the set commands to the temporary store, or the del command by setting to be deleted after transaction to be true. All right, and after all the commands are applied, if we want to abort, we can skip the dumping step and just return back that the transaction is rolled back. But if we are committing the transaction now, what we can do is we can dump the cache into the original hash map, and as I told you, we will copy the keys from the temp store into the main store one by one. And while copying, we'll check if the value is set to be deleted, we'll remove it from the primary store. But if it's not, we'll update the value in the primary store according to what the value is there in the temporary store. And then and only then can we unlock the original hash map, and then we can say that the transaction has been committed. Okay, so that's the entire process of the transaction. And I think I'm going to do a small marathon of sorts and write the code for all of it in one go. So the next video might be a long one. Let's see how I decide to do it. I may break it down, I may not. So I guess that's it for this one. I'll share the link to this escalator diagram. I'll update it a little and share this in the description. Look out for it. And that's it for this video. I'll see you in the next one.